Great, thank you. So I'm really excited to be giving this talk. I also look forward to the future when we can do this in person. If you have any questions, feel free to drop them in the chat. If I don't get to during the talk, I'll stick around a little bit after too, so we can chat then. Today I'm going to be talking about Kubernetes and how to get started with stateful applications in Kubernetes. But first, I'm going to do a little bit just to give an intro about myself. My name is Tom Manville, founding engineer at Kasten, as well as director of engineering at Veem. My previous job was at Dropbox, where I worked on a giant sharded database service built on a very large cluster of MySQL databases. I attended my first Percona Live in 2014, and I've enjoyed it many years since. A little bit about Kasten. So Kasten's goal is to help simplify data management in Kubernetes, and we have several projects that are in the open source community, as well as some proprietary software as well. Around 2 years, we started a partnership with Veem. Veem is a company that does data protection for many types of infrastructure. And since then, that partnership has blossomed into an acquisition. Kasten is still largely independent, but we have some pretty cool integrations coming out soon, so keep tuned for that. We're hiring very aggressively, and so if any of the topics in this talk seem interesting, please reach out, check out our hiring page. We have a ton of openings across sales, marketing, engineering, and feel free to reach out to me directly for any engineering roles as well. So first, what I want to talk about is containers, because they're kind of the basis for Kubernetes. Containers are lighter weight than VMs that share a common kernel amongst multiple instances of the container. Containers are packaged by stacking immutable file systems in layers that contain libraries, binaries, and configurations. Containers are run by invoking some binaries inside the container. And typically, the lifecycle of a container maps to a single process, but you can also run multiple processes in containers if needed. These properties make it very well suited for developing and running microservices. Containers can be run locally, but if you're going to use them for production applications, you should really use a container orchestrator. And of course, Kubernetes is the most popular and successful orchestrator out there. It started as a project from Google. It's entirely open source, and it contains a lot of learnings from Google's master scheduling systems, namely Borg and Omega, as well as a huge community and tons of contributions since then as well. When using Kubernetes, you provide it with your underlying infrastructure, such as compute nodes and storage and networking equipment. And then Kubernetes will schedule all of these resources for you and provide common abstraction, making it easy for many people to lift and shift their applications to different types of infrastructure, for example. A good analogy for Kubernetes is Linux. Like Linux, Kubernetes provides a common abstraction for your infrastructure. And there's also several distributions of Kubernetes that you can try. Some of them are open source and free. Some come with support licenses as well. Kubernetes was donated by Google to an open source organization called the Cloud Native Computing Foundation as its founding project. The Cloud Native Computing Foundation, or CNCF for short, is a group of projects and companies that share a common vision on how to improve the cloud native ecosystem. Since then, the ecosystem has exploded, and the community has donated many more projects. Projects go through maturity phases, and they're given a maturity level depending on their compliance with best practices, their reliability, and very importantly, their adoption. They need contributors from different companies. They need some specific metrics for popularity as well. This slide is going to be a little bit overwhelming, so don't get overwhelmed, but there are many, many projects and companies in the cloud native ecosystem. You can find many really interesting projects in here, projects that maybe existed even before CNCF that were donated to the foundation as well. If you look here, I'll give you a second to try to find the Kasten logo. It may be a little bit difficult because there's so many projects. And so for that, I'll help you out, because when I did this, it took me actually a while to find. So one principle that's well supported by Kubernetes and CNCF projects is that infrastructure should be configured as code through declarative APIs. Kubernetes has a well-defined set of best practices around these APIs. And these are applied to the core APIs for Kubernetes, as well as recommended for any third-party extensions. And Kubernetes is a pretty advanced extension framework, which I'll get to in a second. Most APIs have a spec field. So a spec field is where users can declare their desired state. When they create this object, it goes into the Kubernetes database and etcd. Kubernetes controllers will see this object, and they will try to enforce that state. And any changes they make will be updated in the status of that API object. Here you see I have YAML for these objects, which is a pretty common format for these APIs. If you opt into these guidelines, you get a ton of ecosystem support, and it lets you consume and get updates around these APIs through a standardized set of command line tools, as well as SDKs in many different languages. So Kubernetes application is actually composed of many of these individual API objects. And so everything from networking configuration to storage to the actual containers and themselves are defined in these API objects, and Kubernetes will go and schedule these. Applications can get pretty complex, however, and so it's usually best practice to check these API objects into your Git repo or use some kind of package management. My favorite package management system is Helm. Helm is really two things. It's first a templating system that lets you specify parameters to go and render a bunch of YAMLs for these API objects. And it also has management operations. So it can handle some of the lifecycle transitions of your applications as well, depending on parameters you set. Helm includes several repositories of many of the common stateful applications that you know and love. And you can parameterize all these things, as well as perform kind of some of the more interesting lifecycle operations like scaling them up and scaling them down. The number of applications in Helm repositories is too long to list here, but here's some of the common ones. Percona, for example, also has released some resources for Kubernetes. It uses an API extension called the custom resource definition. When you create these objects, it actually lets you extend the Kubernetes API, and so you can perform any type of operations exposed through the system that Percona provides. This example, I just wanted to show what a custom resource definition looked like, and this is a snippet from Percona's. There's actually several of these. In this case, this one is just for instantiating an extra DB cluster. As you can see, I can then go use kubectl to go and check the status of these clusters if I have any. I also want to talk about volumes in Kubernetes. There are many different types of volumes you can support. You can use distributed file via something like NFS. You can mount block devices from SAN arrays. You can consume disk directly attached to your nodes, various mechanisms. By default, Kubernetes will actually install file system for you on any block devices you add, and it can handle things like resizing by changing those API object specs that I showed you a little bit earlier. Direct access to block storage is also supported for some of the databases that can use that. One of the reasons that Kubernetes has been so successful is that it really understands what the roles in the cluster are. And Kubernetes resources and their permissions are grouped into namespaces. You can limit the scope of users to specific namespaces and even specific API actions within that namespace. Limits can be placed around the number of resources, for example. You can really clamp down on the APIs that individual users can run through the Kubernetes RBAC system. Cluster storage or database admins will usually have much broader permissions akin to sudo access in the traditional world. Despite the different roles, Kubernetes also has storage mechanisms that allow developers to request and set parameters in the storage they like. So let's look at how that is set up. Two of the main objects here are persistent volumes and persistent volume claims. Persistent volumes, or PVs, are objects that are defined by cluster admins. They can contain enough information to directly represent some underlying volume. Because of their scope, PVs are actually not tied to a namespace, but are at the cluster level. Persistent volume claims are a user request for some of that storage and can contain several parameters. If any of the matching criteria in the PV matches in the PVC in the claim matches a PV, then that PVC will get bound to that PV. If you don't want to pre-allocate all of your PVs that you might possibly need, you can use dynamic provisioning. Dynamic provisioning lets you define another API object that contains several parameters for anything you need to provision and mount storage. You may want, you'll have to make sure you have enough space, and you'll want to watch how much storage you actually get allocated here as well. On the provider side, there's the container storage interface. So the container storage interface is actually the culmination of work from many different orchestration communities, including Mesos and Docker Data Center. This interface is something that providers go and implement. And once users install drivers for that provider, they can then use Kubernetes APIs to consume that storage. And most major block systems support CSI, and so you can usually just find the driver that matches your storage needs. Optionally, providers can implement the snapshotting interface in the CSI. And if so, then users can actually use Kubernetes APIs to go and take snapshots of volumes. It's important to note that the behavior of a snapshot may vary depending on the underlying storage you're using. So for example, if you're running a cloud provider, the storage may be very durable. So for example, EBS, when I take a snapshot, the snapshot is stored in S3, which is off cluster. This may not be true for local storage systems or storage boxes that you're running on premises. And so the properties of those snapshots may be different, and take care to understand the reliability primitives there. So using storage in Kubernetes is actually quite challenging, and there are many configuration settings that you have to set up. And this is due to its flexibility, as well as the large number of contributors to this ecosystem. So there are numerous providers. I think last I checked, there was over 100 providers that have implemented the CSI interface. And so due to this large number, it can be tricky to correctly configure these. And of course, the cost of failure is quite high. If you incorrectly configure your storage, it may be the case that all of your containers get stuck. And so that's obviously extremely costly. To kind of help with this, we've actually released an open source project called Coopster. It's completely free and open source, and I encourage you to check it out. The goal of Coopster is just to help check to see if your storage is configured correctly. It also does some benchmarking to see if your performance is where you expect it to be. We also have a few other open source projects as well. One of my colleagues will be giving a talk on Canister relatively soon. In fact, it's in roughly an hour on live. So definitely check that out if you're curious. Canister lets users define APIs that contain scripts for performing certain operations. So you can kind of bring your existing database scripts into Canister and then use all Kubernetes native APIs to perform operations. We also have Copia, which is our backup platform. We didn't originate this project, but we're a pretty large contributor, and we're a big fan. It helps you store any types of backups or snapshots in object storage. And so with that, I want to say thank you. We have some time left, and so I'd love to take any questions that you have. So please just drop them in the chat, and I can kind of go through them there. So one question we have here is, are there consistency guarantees provided by CSI? And the answer is no. I think you can imagine providing snapshot capabilities on many different types of storage systems, some of which may not provide very strong snapshot guarantees. Off the top of my head, there's a pretty popular one in Kubernetes systems called Ceph. The consistency guarantees with Ceph are slightly, I'd say, relaxed compared to the guarantees provided by something like EBS. When running backups, when taking backups in Kubernetes and using snapshots as a primitive in that, it's important to make sure that you understand the consistency properties. One thing that Canister helps do is let you run scripts and tools to, for example, quiesce your database. So another question we have here is, what is the persistent storage solution recommended for RDMS? There are actually many different types of storage systems. If you recall that the slide I showed on the ecosystem, there's a ton of projects that are focused on Kubernetes or have support for Kubernetes. And so that's actually this section here. in that slide. So let me share my screen really quickly again, just to show this. So this is the landscape, and as you can see, there's many different kind of cloud native storage solutions, or storage systems that support cloud native workflows as well. And so it's a pretty complex process to go recommend one of these. My products that I work on are not directly primary storage, but they do help back up and implement data protection workflows around these storage systems. So definitely reach out if you have questions. We can help you evaluate your different storage systems. I also recommend looking at Coopster, because Coopster will help you benchmark the storage systems that you want to set up as well. Of course. Awesome. Doesn't look like there's too many more questions. If you have anything else you'd like to ask, I'm going to drop my email in this chat, and feel free to reach out for any questions on storage systems. I love just discussing kind of any challenges you're facing and anything like that. So I'll put that in chat here. And I'll hang out for another couple of minutes. But I want to thank you for your time. I appreciate you attending, and I look forward to hearing from you with any further questions you have. So thank you. Great. Thanks, everyone.